This is lesson 6-2, and this is on exponential functions. By the end of this lesson, you should be able to state, I will be able to describe and graph exponential functions. The terms you'll need to be familiar with are exponential function, constant ratio, initial amount, and asymptote. So let's look at the difference between a constant rate and a constant ratio. A constant rate is something that we saw when we saw a pattern that was like addition. So for example, each time x increases by 1, y here is increasing by 2, plus 2, plus 2. Over here, x is increasing by 1, and the output is now doubling. So it's times 2, times 2, times 2, times 2. So when we have a pattern where the rate is increasing as an addition or additive relationship, it's called a constant rate. When we have the pattern in the table and our y values are increasing multiplicatively by multiplication, that is called a constant ratio. Let's try this one. This one is times 5, times 5, and times 5. So again, this one is going to be our constant ratio. And this one, plus 6, plus 6, plus 6, will be a constant rate. Let's look at what this looks like on a graph. Here we have the function 2 to the power of x. We have a table of values, and we typically use the values from -2 to +2. This extra 3 in here is just to give you another data point. But we're going to need to substitute in our x value into our exponent and then evaluate it. And this is why we had to learn our exponent properties so that we could properly apply the function and graph them. So here we have the exponent -2. Remember that a negative exponent tells us that we need to write it as the reciprocal. So this becomes 1 over 2 squared, or 1 over 4 when we evaluate that. And we need to actually evaluate it because we need the actual input or output for the graph for our x and y values. Let's do -1. 2 to the power of -1 is going to be 1 over 2 to the first power, or just 1/2. 2 to the power of 0 gives us 1, because any number to the power of 0 equals 1. 2 to the power of 1 is 2. 2 squared is 4, and 2 cubed is 8. Now, let's make the connection between ratio and a constant ratio and a constant rate. Here it is being multiplied each time it's increasing times 2. So this is what a constant ratio is we're dealing now with an exponential function instead of a linear function like a constant rate. So let's graph this. We have our x and y values. Our first point is -2 and 1/4. So that's right about here. -1 and 1/2. 0 and 1. 1 and 2. 2 and 4, and 3 and 8. you should start to see these values really jump up as your x values increase when it is going in a positive direction because the 2 is positive. So when we connect these, we show that it extends forever infinitely in both directions. And we now look at the characteristics. Well, it looks like it has a positive incline going up here, and that could be because this 2 is a positive and not a negative. Maybe if it's a negative, it's going to go down this way. We'll have to see. We also can see that there's this line here that's coming really close to the x-axis, and I'm wondering if it's ever going to hit that axis or if it's going to just get closer and closer to it. The other thing is we notice our points get farther apart as we continue down the x values here. They get more spread out. The x and y values are more far apart. So those are the characteristics that we see. Now let's look at the word asymptote. The asymptote is the line that the graph approaches but never quite touches. Let's connect these. And remember, this was the graph of what we just did. So we can see, we connect them. Well, it must be referring to this x-axis. This line right here, where it looks like it's going to hit, is actually never going to touch the x-axis. That's called the asymptote, right here. So this part is the asymptote, and it is going to look like it's going to touch the x-axis, and it's going to get infinitely like as close as possible, but it actually will never hit that point, which means that x equaling 0 is never going to be a true point on this graph, on this function, because the x-axis is where y equals 0. Okay, so now it's your turn. You're going to graph this function, f of x equals b to the power of x, and the b equals 1/2. So you can see here that that's been filled in for you. It's 1/2 is your base number, and you're taking that to the power of x. So let's first look at what that would look like. Here's 1/2 to the power of x when x is -2. Well, remember that if a base is already written this way, we can think of it as being written as 2 to the power of -1. That's what 1/2 is. This negative pushes the 2 to the denominator, and the 1 means it's just a 2. So now let's look at this in terms of 2 to the power of -1 times the power -2, because it's power of a power. Well, that then means that this is now +2, so now it's 2 squared, which means it's 4. -1 for the x, I'll do one more, is being taken to, no, that's the exponent, 1/2 to the power of -1. Again, this is the same as 2 to the power of -1, and then raise it to the -1 power. That results in a +1, so it's just 2. And you should start to see a pattern here, but keep working through just to make sure. It looks like we're now dividing by 2 every time. Think about that. Also, I'm wondering, is this going to still result in an uphill slope going this way, or is it going to come down this way? So go ahead and finish these. Remember that 1/2, it's best to write it as 2 to the power of -1 and then distribute your x value to it. Pause the video, work through that in your math notebook, and then come back and check to see how you did. So here's what yours should look like. If you continued to write 1/2 as 2 to the power of -1, and then you took it to the power of 0, that would be 1. Any number to the power of 1 or 0 is 1. And then a half, and then a fourth, and then an eighth. So it does look like what we're doing each time is dividing by 2. Every single output. Now, look here. It did result in the line going this way, negative first. Our asymptote line is right here along the x-axis, where it's never going to touch it, but it's always going to get closer and closer. And so thinking about this, we didn't need a negative value here as our base. We needed a value less than 1, right? We needed a fraction. Here's a real world problem that we can apply. A network administrator uses the function f of x equals 5x to model the number of computers a virus spreads to in x amount of hours. If there are 1,000 computers in the network, about how many hours will it take for the virus to spread to the entire network? So here we can see that our function is 5 to the power of x. This should have been raised up, by the way, to an exponent. This is 5 to the power of x. And so we're going to do the same thing. We have our base, we raise it. Any number to the power of 0 is 1. This would be 5. This would be 25. This is 125. This is 625. I'm not sure, but I want you guys to finish this, graph it. Again, you're doing this table and the graph in your notebook, so you have a real world example. And then it's asking how long is it going to take for the virus to spread to 50,000? This was if there are 1,000 computers. So we'll check back on that, but let's just practice being able to apply the function, create the table, and plot the points. So here's what our graph looks like. We can see how quickly this really starts to shoot up and how fast. Noticing that it probably has to do with this base of 5, right? The lower the base, the kind of wider we have a slope, I guess you could call it, right? But the larger the base number, the steeper this exponential function is going to grow up and shoot up, okay? It's asking about how long would it take for the virus to spread to 50,000 computers. So here's where we know the output. The output is the number of computers. So what we want is to fill in the output for this. We could do the same thing for 1,000. How long will it take for the computer to reach 1,000? Now, we don't want to necessarily guess this number here because we didn't have exactly 1,000 computers here in our output. But if we know the output and we know the function, then we can figure this out. Now to solve this, we would need to take the x root, because this is the exponent, of each side, but we still wouldn't get any closer to solving this side. So on our graph, we can make an estimate and check it. If we look here, we can guess that this is about maybe 4.3, just of where we kind of lifted it up here. And so if we check that, assuming most of you would be using a phone, you would do 5. Your XY button gives you your root, and then we're going to guess 4.3. I think that's pretty close. We can leave it at that. It's a little more than 1,000, and that's what we were asking for. So the answer to this question, when it's 1,000 computers, would be about, and we show that with a squiggly equal sign, 4.3. 4.3 what? 4.3 hours. How many hours? That's what we were talking about. So we put that context in the answer. Now looking at how long it's going to take to spread to 50,000, we can see that this is jumping up exponentially, very, very steep, very fast. So at this point, we can just make some guesses. 5 to the power of, we'll try 5. 5, we already knew that one, so we know it's bigger than that. 5 to the power of 6. 5 to the power of 7. Oh, that's way more. So it's got to be somewhere in between 6 and 7. So we just keep trying. That's 29,000. We need something bigger. 5 to the power of 6.6. We've gotten pretty close. I'm betting that 5.7 will be too, or 6.7 might be too high. Oh, no, we're getting closer. So around 6.7 would affect about 50,000 computers. Just pay attention to where your decimal is. So that's the strategy there. So an exponential function is the product. We'll save this one for later, actually. Pause there.